With improper integrals, we've been actually trying to get to one specific point of this unit. It's not really necessarily evaluating limits or integrals that go to infinity and negative infinity and just continuities. It's actually more so towards this idea of comparing integrals, especially with those that go into infinity, because some actually approach to a value, some go to infinity. And how do you know, especially with functions that you don't know the integral of, how do you know if they converge or diverge? So this is kind of like the second part of the improper integrals. So the first part was actually just evaluating it, which was good. And then the second part is about comparing them, which I find a little bit more interesting. And especially the way it's set up. They set it up in such a way that it kind of looks interesting when I first looked at it the very first time. We want to define something very specific. Specifically, g of x is always going to be bigger than f of x, no matter what, for this interval. So any value between a and infinity, including a, g of x will always be greater or equal to. The idea here is that if I know that the integral g converges to a value, since g is always bigger than f, then that same integral of f should also converge. We don't know the value it converges to, but we just know for sure it converges. And I guess we can flip-flop it. Since f is smaller and I know f diverges, g should also diverge because it's a bigger function, if you want to think of it like that. Since f is smaller and it diverges, g should also diverge. So that's the idea. And we typically use it with functions we don't know the integral of. And we're going to look at one example right now. I guess probably one of the most important examples, especially like in a book, that a calculus book, is that they tell you that there's many integrals that you can't find the integral, or many functions you can't find the integral of. So I want to find this integral, or not really this integral, but I want to find if this actually converges to a number. And we cannot find the integral of this using anything we've learned so far. I don't even think it's possible with my knowledge, and I'm pretty sure it takes some advanced mathematics to even be able to think about what this is, and I feel like they had to define something new that's outside the realm of calculus to even find the integral of. So the question here is actually not what's the value, it's does it converge or diverge? And this is a hard question already because we can't find the integral, so what can we do? Well, we can compare it to another function. So the function, it might take some thinking critically about it. The function I want to compare it to is actually, so we want to compare this function to something, I guess we can do it to something bigger. And that function is namely e to the minus x. So we're going to look at a graph of these two and see why this value, this function, is always going to be bigger. So we hopped on to, I guess, Desmos, and we're going to be looking at why e to the minus x is actually bigger than e to the minus x squared. So here's e to the minus x squared. It's a very, I guess it kind of looks like a normal distribution if you know some statistics. It kind of looks like a bell curve, in other words. And I made it so that this function will always be, if I were to add this in, notice that any point after 1, right, the bounds were 1. So any point after this blue line, which is e to the minus x, will always be, here, let me actually scroll this, right, so this blue line here will always be bigger than this one. So that's the idea of comparison. We want to just compare it, so back to the whiteboard. This is true, so if I know that this converges, I know that the overall integral that we were looking at converges. So let's see if this converges. This is the limit as b approaches infinity, b1 e to the minus x dx, which is equal to limit as b approaches infinity of, let's see, minus e to the minus x evaluated at these two, which is the limit as b approaches infinity of, I guess, let's see, minus e to the minus b minus e to the minus 1. I'm going to scroll down. This is equal to limit as b approaches infinity of, let's see, minus 1 divided by, this is a negative, so I'm going to change it to a positive exponent, and then minus minus, that's plus e to the minus 1, which is equal to, this goes to 0, so we're left with e to the minus 1, or 1 over e. In other words, this converges because it's a value. So the point I want to make here is, I'm going to zoom out first. The point I want to make is, since e to the minus x is always bigger or equal to e to the minus x squared, and the integral of the one that's bigger converges, that means the integral of the same bounds, right? The same thing also converges through the comparison test. So I'm going to write that via comparison test. And that's all the work you basically have to show. You actually have to kind of make this statement at the end too to prove your point. So just a basic recap, I guess. We wanted to find the integral if the integral of a function we don't even know the integral of, if it converges or diverges. And the way we went through this is actually comparing it to something that's bigger for that interval, 1 to infinity. And I found when it's e to the minus x. And in this case, I can actually find the integral of e to the minus x, and that's a very simple process, which I showed here. And I found ultimately it converges. And that tells me one key information. Since it's always bigger than the other function that we are looking at, bigger than this one, namely, and the bigger function, e to the minus x, always converges on that interval, then this one should also converge. And that's the whole premise of the comparison test. Here we go, second question. Determine if this function and this integral dx converges or diverges, right? We don't have to find the value of it, we just have to find if it converges or diverges. It's a very weird looking function. Let's actually kind of simplify it, or kind of manipulate it just to make it look a little bit nicer. So I'm just going to rewrite this. As the integral of let's see, let me just write it out here. So I want to find this integral for, so I kind of split the fraction, and we can do this because it's an integral property, right? The sum of the integrals is basically the integral of the sum. So this is actually a minus sign. Let me clarify this. Minus sign, sine 3x over x4 dx. And now we can actually start looking at it since it looks much nicer. Let's look at the first part. So I'm just going to go quickly through this one because this one actually, well, let's just look at it. So limit as b approaches infinity of 4 for x to the 4th dx. Oops, the limit of 1 goes to this. Let's see, what is this integral? We can just do, let's see, integral, let me just do it here. It's the integral of, what's this? Oh, sorry, x to the minus 4 dx is equal to, let's see, you add 1 to the exponent and it's negative 1/3 x to the minus 3. In other words, and then we just bring the constant over. So it is 4 over 3 negative x to the minus 3. Let me just double check that one. Yeah, that sounds about right. Evaluated at 1 to b, right? Oops, this should be now b. There we go. And it's the limit, I forgot that. B approaches infinity of that. And let's see. We get negative 4 over the limit as b approaches infinity of negative 4 over 3 b to the minus 3 minus negative 4, 3, 1 to the minus 3. This one goes to 0, and this one ends up to be a number, so we know this converges, right? I don't really care about the value it is, I just care that it converges because it's a number. Now let's look at the second part, which is actually the thing that requires the convergence, not the convergence, the comparison test. So let me just look at the integral solely. I know that this function sine of 3x can only be going, the greatest value can be 1 and the least value can be negative 1. That means if I were to divide everything by x to the fourth, this integral in the middle will always be smaller than this bigger integral, which is 1 over x to the fourth. In other words, this is what I'm going to be comparing to, and you might be able to use this idea, especially with when a thing with a power is on the bottom. You kind of usually powers are something over the power is always the best thing to compare it to, and so a 1 over x to the fourth. And I'm actually going to go through this really quickly because we actually did something very similar right here. There was just a constant on top, right? And we can just take that constant out, right, in that case. But here's the actual thing. Since I know from the work right here, this converges to a value, right? Since it's 1 over x to the fourth is pretty much the main function, I know this converges already because of my work above. It converges to a number. And the point I want to make here is, since the two integrals converge, the sum of the integrals converge, right? We just add two converging numbers. And that means, what does that mean ultimately? That means this integral converges. Via comparison test. So this is what we use a comparison test for. We use it for integrals we don't know the integral of, and we compare it to something that we do know the integral of, usually some sort of power, something over x to the power. And we're actually going to be continuing this idea of convergence and divergence when we get into infinite series, so we have to be really comfortable with the idea of converging and diverging, especially before we get into infinite series, which is a very, I guess the way I can say is a very difficult unit. So hopefully you get used to this idea of comparison test. But I'm going to go back to the main idea, the comparison test right here. Right, we want to basically define or have a function that's always bigger than something smaller, and that allows us to compare two comparisons, right? And it basically tells us if something converges that is bigger, then the smaller function should converge. In contrast, if the smaller function diverges, then the bigger function diverges as well. So that's the idea of comparison tests, and that wraps up improper integrals. So if you have any questions, remember the forum is always there. I can always make a video on improper integrals, especially with the comparison test, because I guess I can never get to every single problem, and every single problem has its own unique twist to it. So if you're very confused, you can always send a problem and you just fill out the form, and I'll most likely do it almost as soon as possible when I have free time. So that's the idea of this, and that's the end of this video. Okay.